Okay, so our next speaker is Andreas from Krakow, and he's going to talk about inflationary dynamics of non-minimally coupled f of R matter curvature theories. Maybe I'll send you a reminder when 5 minutes are left.
Great, thanks. Is it okay to go on? Start?
Yes,
okay.
yes.
Okay, great. Hi, everyone. Thanks very much for the invitation, for having me. I'm Andreas. I just started my postdoc here in Krakow. I was before in Portugal, where I worked with Orfeo Bertolami and his PhD student, Miguel Barroso Varela, on this topic. So you can find the paper and so on. So we looked at this non-minimal coupled matter curvature theories that I will tell you a bit more about their inflationary dynamics. So just to have like a very quick introduction overview of what we're talking about. So we're talking about cosmology. We know very well what is going on in the late universe with accelerated expansion and dark energy and so on. But going back towards the past, we have a fairly good understanding of what is going on up until the Big Bang, where you have Big Bang nucleosynthesis, and when the photons decouple and you emit the CMB. But really, what is going on before that is not very well understood, as shown here in this picture. So there's this postulated, this is the favorite paradigm for the early universe, where you have this period of exponential expansion, inflation in the very early universe that solves your problems from the hot Big Bang model about the flatness, the horizon, and the relic abundance, right? And then the connection of how you get from that to actually the radiation domination through reheating or something else is a bit less well understood. But the point is that really we can understand what's going on here, and we have some indirect or different ways to look in the early universe. One very famous is gravitational waves that travel unhindered after the production. So this is one way to look into that, although I'm not going to talk about gravitational waves in this case. So through this analysis of these theories, I'm gonna talk to you about kind of looking at these earlier moments. Of course, inflation, as many of you know, is very successful because it gives you a mechanism to take the initial quantum fluctuations, stretch them to super horizon scales, and then when they re-enter the horizon, they evolve classically and they seed your large-scale structure in the late universe, your galaxy formation, right? So this is one of the key attributes, and this is what gives you, this correlates with the CMB and isotropies and so on. Okay, so to motivate about this theory, so this non-minimal coupled matter curvature theory is originally proposed a long time ago in the 70s and 80s by Gunnar. It was purely theoretical endeavor, mainly from this kind of modified gravity perspective. And that in these papers, the interest was to find the mass limit larger than the black hole mass in GR, but then they were kind of looked upon more carefully as the field evolved. And of course, the main motivation was to get a dark energy mechanism without putting scalars by hand. Then there was also motivation to explain the extra force, to explain the galaxy rotation curves. There was the pioneer anomaly at that time, and whatever, there are the initial papers, but there were many more afterwards where you study these theories for, as I said, for late time acceleration, but for Hubble tension, the perturbations, structure growth, even gravitational wave polarizations, and Miguel and Orfeo have many papers on that, and the collaborators, and you can look into them. But one thing that was relatively unexplored, apart from this paper, was what is the impact in the early universe, especially because when you're talking about non-minimal coupling between matter and curvature, it is important during inflation because you have high curvature scales. So our motivation was kind of revisit this regime in this paper and kind of go look deeper into that, and we actually updated and corrected some misconceptions that were in that paper and went a step ahead to improve on a lot of things. So let me kind of gently introduce what we're talking about NMC theories. So you start with your action. Now you're generalizing your gravitational sector now to an f of r function here, function of curvature, and now in front of your matter Lagrangian, you're putting another function f of 2 of r here. Right, in the GR limit, to recover GR, you just put your Einstein-Hilbert term for f of 1, f of 2 you just put to 1, and that's your GR limit. But now you're generalizing to going beyond. And you're going through the usual game where you're varying the action with respect to the metric to get the Einstein field equation, which now looks much more involved. And you're just taking the conservation of the field tensor, and now your modified conservation equation is also more involved. Now you notice we write everything in terms of these capital F's. So this indexed capital F is just the derivative of the small f in the theory, right? With respect to curvature, and this indexless capital F is just this combination. But as you can see here, just mentally doing the GR limit comparison, the f of 2 goes away and you recover the conservation equation. And similarly for the Einstein field equation, you just recover g mu nu equals t mu nu, because this is r minus r, derivatives of a constant. F2 is 1, capital F is 1, so g mu nu equals t mu nu. This is the GR limit. But this is just an exercise to show you how much more complicated things look when you generalize and exactly where the new terms will come from. And naturally now, since we're talking about cosmology and inflation, you take the Friedman equation and now your Hubble rate similarly looks much more complicated rather than just being rho over 3, right? You have all these other terms. And in fact, this is one of the key ways where this will affect your phenomenology and your predictions and so on. Okay, so moving on, I mean, when we're talking about this inflationary space-time, you're usually assuming homogeneous and isotropic universe. Your whole matter content is dominated by the inflaton, and you are modeling this as a perfect fluid with an energy stress tensor with energy and pressure here. And your matter Lagrangian for the inflationary field, it's a scalar field, so it's the usual thing that you have the kinetic term minus the potential. Now you notice here there is this parametrization in terms of beta, and this has to do with the choice for the matter Lagrangian that is an inherent issue in these NMC theories, because the choice matters in a lot of these studies. We kept this issue here, even though, as I will show you and you will see later on, it doesn't really affect the inflationary dynamics, but we kept it just to be consistent and to be able to generalize it and look more into that. So now taking the Friedman and the Raychaudhuri equations, you can obviously see that they look very similar. So apart from a minus sign, which is to be expected, this is the usual equation of state for inflationary universe when you have this exponential expansion, up to derivatives of f and h, which in slow roll, as I'm gonna show you later on, this go to 0. So you recover this equation of state, inflationary equation of state, which is good news for you, right? These are constant during slow roll, as I will illustrate shortly. And going on, I mean, you can write the continuity equation of motion of the inflaton, and you just notice that you get this new terms, the friction term from the F2 that goes against your Hubble, right? Here, and here. But the point is that even though in the early universe your curvature decreases, right? So you get a negative here, and you can potentially have effects against the Hubble drag during inflation, during slow roll. This is so small that it doesn't make any difference. So in this case, it won't make any difference, but it will be important towards the end of inflation and going in the post-inflationary universe. And in fact, we did the full calculation beyond slow roll. So Miguel very successfully, did a very involved numerics where you solve the whole thing, and there's a whole section in the paper where he describes how this happens. So this is really carried through on, but in fact, for the results, you can in this case you can stay within slow roll. So as I mentioned, this is the matter Lagrangian choice is relevant in this, but might be important towards the end. And in fact, this is how we started looking into that before focusing on inflation, because there was already quite substantial results there. So you can expect significant NMC effect during kination and into reheating, and this is something that we are working on as the sequel, and since the machinery is there. Okay, so now maybe to explain a bit slow roll, since I mentioned it so much. So this is the usual picture now in the current inflationary paradigm called new inflation, where you have a very long plateau in the potential of the inflaton phi, where the inflaton is very slowly rolling. So the energy density is approximately constant. The inflaton velocity is very small. And this is the part where you have exponential expansion. All right. At some point, inflation needs to end. So slow roll stops being true, and you have some fast rolling, some kination, and depending on how your potential looks like here, you can have some oscillations that then allow you to reheat in the hot Big Bang universe, or some other mechanisms. This is the idea. And in GR, slow roll implies exactly that the time derivative of the Hubble rate is 0. So this is have to be cautious here about what this implies for GR and for NMC, as I'm gonna show you later on. But just taking this kind of more naive perspective that it is just this in the NMC, you can write your Hubble rate, which was, I showed you, more involved before, in a kind of more simplified manner. And up until here, you've been seeing a lot of the indices, and things are complicated because I haven't decided on a model, on a theory. So let's do that to make the calculations more specific, but you can put whatever you want. So in our case, for F1, we stick with the GR, the Einstein-Hilbert term, and we just change the F2. So we use a power law term for the F2 with plus and minus signs here, so equation 11. And you have an NMC scale M below the curvature to normalize it. So with this choice, when you're looking in the slow roll regime, where the Ricci is 12 times the Hubble rate squared, you recover the energy density as a function of the Hubble rate that looks like this. And already here you can see that for n equals 2, you just recover GR, so the inflaton is decoupled from the theory. You can go ahead and plot this, so you can look how the energy density scales with Hubble rate in the positive and negative case of theories. It's important to make this distinction, which was not done before, and I will show you later on why is that. But it really, as you already see, it makes a crucial difference on what is the range of the valid scales for the inflationary scales and the energy densities. And in fact, from the previous expressions, you can get some bounds on the inflationary scales and the energy density that play a role and actually allow you to constrain your theory. Okay. So in NMC, the slow roll does not plainly imply h dot equals 0, but through the equation of state, it really implies that this expression should be true. And this is nothing else than when we're looking at these equations here, just by making this obey the slow roll, the equation of state, is just matching the extra terms to get 0, right? And in fact, what this gives you is this third order differential equation, this very convoluted system in this theory. Right now, you have something more general if you don't want to plug in your f of 2 here. And in fact, to see if h naught is a solution here, you have to solve this system. And this is something that we went beyond from the previous study. So you can treat this as a system of differential equations and you're looking at the de Sitter solution, right? And by doing this analysis, you find the solution h dot equals 0, but the stability of this solution is not trivial to see. So one eigenvalue is always 0, but then in order for the solution to be stable, the other eigenvalues, the real part of the eigenvalues, should be negative. And you see in these plots here on the left side, where it's for the positive theories, that you always have a positive L1. So that means that this solution is unstable. In contrast, in the negative theories, L1 and L2 are always negative up until some threshold of the inflationary scale where they cross 0. So this is the validity of the theories, and this should abide with the previous bounds that I mentioned before. So this was already a surprising result, because in the previous study, they just assumed the plus sign in the theory and that solution, but in fact, it's not stable. And this has some analogy with these Dolgov-Kawasaki instabilities, where you assign an effective mass on your propagating degree of freedom. In this case, it would be proportional to the FDR, and this has to be positive. In this case, now this quantity is proportional to this quantity. The matter Lagrangian is minus rho, so this is negative. So then that means that this should be negative. And the only way for this to be negative is to have a minus sign in your F2. So also from that, you can see that the plus. So they are completely ruled out. So you're only left to play with the minus ones. So half of the theories are not valid. All right. This was already surprising. Now looking at the phenomenology and the predictions, so how the NMC theory will affect your CMB observables. Since the perturbations are produced during slow roll, they behave classical, follow the GR evolution. And you, because everything is so deep in slow roll, you don't get any effects from the friction, from the Lagrangian choice, from the effective mass of the Infilton, and so on. The only effect you get at the power spectrum is just from the modified Hubble rate here. So this is, if this expression in GR, this just gives you 1. So it's the usual one that you have in terms of the slow roll parameter. But here, this is not 1 in NMC. You have a more involved expression, and this is how it will change the prediction. Same is true with the spectral index. Do the usual calculation, but then you have these terms that do not go to 1 as in GR. For the tensor sector, you don't get any contribution in the power spectrum, but in the spectral index, in the similar way you get from the Hubble rate, this contribution here. And then going to the tensor to scalar ratio, you get this similar. I mean, it's just straightforward to do. Again, the NMC Hubble rate is where things get affected. So before showing you the plots, just a final note on the inflationary scale hierarchy. So you have the pivot scale where the CMB observables are produced, and you have this maximum inflationary scales that I showed you before that are the threshold of the theory, where the eigenvalue is still negative and you can trust it. And your inflationary plateau scale should be somewhere in between there. So you can now constrain your theory, since this is a known value written here in terms of the tensor to scalar ratio. So by taking the expressions from before, you can come for a lower bound on your NMC scale, which is the typical inflationary scales. And this makes sense, as it normalizes the curvature scale at that stage, and it becomes less significant as time goes on. In the same way, now you can look at the inflationary plateau scale and look that you can, for your model building, if this is useful for whatever model, you can get a lower scale of the inflationary plateau depending on the n index that you go in your theory. As you go at higher ends, you don't get much difference from the previous predictions, but I mean, for practical purposes, we stay within the n equals 3, 4 to show the results. Okay, so it's much better to look at the plots and see what they actually predict. So I did for a range of inflationary models, but you can plug in your favorite one, whatever you want to do. So for the quartic symmetry breaking model, you can see the prediction. So in red, it's the GR in this RNS plane. You can see the two sets of data. The most recent one here in purple, 1 and 2 sigma variations, and for the range between 50 and 60 folds of inflation, matching the pivot scale of the CMB predictions, right? And you see that going from GR to the NMC model for n equals 3 in this case, at the coupling where everything is well behaved, all of your predictions go to shorter NSs and lower Rs and higher Rs, sorry. So you go further away from your predictions, and that means that the NMC is really not improving things here, which is already not favorable, right? We also wanted to look into monomial potentials, but they were already, again, far away, and this behavior of the NMC would take them further away, so it's not really worth looking into them and showing you a plot about them. Going into more favorable models like the hilltop here, you can see in the quadratic and quartic hilltop models that already GR does a much better job, and the NMC you get a similar effect where you go towards the higher left corner, so shorter NSs and higher Rs in both cases, but you're still staying within the error bars of the predictions, right? Especially in the quartic case. And in the same case, you can treat or you can accommodate natural inflation since it resembles a quadratic hilltop model during slow roll. So your parameterization will change a bit, but for practical purposes, it looks the same. So you can accommodate it here as well. It's more interesting maybe to look at the Starobinsky type potential. It's very much more favored from the data, as you see already in GR within these plots. But now when you're looking at the NMC, it's really not that sensitive for whatever indices here. You just have to increase the coupling strength and to really take it away from the GR, and you see that it goes towards the left. So shorter NSs and shorter Rs as well. So still differentiable result, but here it's much less sensitive to probe. There is a ambiguity here of how you could end up with a Starobinsky potential, because usually you start with a non-trivial F1 of R, right? You add an R squared there, and then you go to the Einstein frame through the conformal transformation, and that's where now your matter sector has been born through this transformation. But so here we just treat just take the potential and assume we are already in the Einstein frame. And finally, when talking about inflationary potentials, we also looked into this old inflation where you have the two minima to see if you can salvage it in the NMC, and the answer is no. You still have the graceful exit problem. You cannot have enough inflation and enough time for the bubbles to percolate from the two different phases. Now, the NMC framework provides you an effective gravitational constant, but so this could, if it was dynamical, it could help give you like an extended inflation model. But the case here is that through this dependence that you get a constant, although different value, but a constant value during slow roll. If you use power law f of 2s as we did, you get weakening NMC effects as time goes on and R decreases. So you cannot really get this dynamic Hubble rate going from exponential to power law expansion in this extended model of inflation. So really you cannot save it. So you have to look at different models. So I think it's good time that I close here. So kind of overviewing what we did. So we looked at this NMC f of r matter curvature theories and generalized to both positive and negative, which wasn't done before. And we analyzed the stability of the solution, which was also just was trivially assumed before, but it wasn't analyzed. And we found that in fact only the negative ones, only half of them, give you a stable attractor solution. The positive are always unstable, so you would never have a stable de Sitter phase. They don't give you viable inflationary models. This was a fully numerical treatment beyond slow roll, but the part that we were interested in for these results was deep within slow roll, but the full treatment was done, and the choice of the matter Lagrange in this case was irrelevant. We saw how what was the interplay between the NMC and the CMB observables. You can bound your free parameter, the NMC scale, right, at slightly above perturbation level. Similarly, for your inflationary scale, you can get a lower bound on it depending on the n index that you have. And as we saw in the plots, the data from at least from these inflationary models still favors GR, but we saw in some cases that there was viable parameter space to have an NMC inflationary model that could be distinguished from GR. So specifically for the Starobinsky and the Hilltop in this case, but can plug in more models and see what happens in each case. And finally, I mentioned briefly that we were unable to salvage all the inflation, and NMC seems to really not help with that. So thanks very much for listening, and I'm very happy to take questions. Thank you.